Today we'll discuss applications of linear algebra to differential equations. It is actually this class of problems that was driving the development of the theory of eigenvectors and eigenvalues in the 19th century. Consider the following problem. We have two functions, x of t and y of t, and they satisfy the following relations, that the derivative of x of t is minus 7x of t minus 4y of t, and the derivative of y of t is given by the right-hand side of these equations. Equations of this kind are called differential equations because they involve the derivative of unknown functions x and y. So what we need to do is we need to solve this system of differential equations. That is, we need to describe all possible functions x of t and y of t such that this pair of functions will satisfy this system of equations. The first thing that we want to do is we want to use matrices. So we're going to write the left-hand side as the derivative of a column vector x of t, y of t. And in the right-hand side, we're going to write this as a product of a matrix with the column vector x of t, y of t. And then so we see that the right-hand side of the first equation must be the dot product of the first row of this matrix with the column vector x of t and y of t. And so we see that the first row of this matrix must be minus 7 and minus 4. And likewise, the second row of this matrix should be 3, 1. Then the dot product of the second row with the column xy will give us the right-hand side of this equation. Now, if we introduce the vector u of t, which is our column vector x of t, y of t, and if we take the matrix A to be the matrix that appears here, minus 7, minus 4, 3, 1, then this differential equation can be written as u prime of t is equal to A times u of t. Next, we want to find eigenvalues and eigenvectors of A. And I'm going to skip the calculations or leave them as an exercise, show that this matrix A has the following eigenvalues. Lambda 1 is equal to negative 1, and lambda 2 is equal to negative 5. And the corresponding eigenvectors are v1 is equal to negative 2, 3, and for minus 5 eigenvalue, the eigenvector v2 is negative 2, 1. This gives us a basis of R2 that consists of eigenvectors. So let's call this B. So it's a basis v1, which is minus 2, 3, and v2, which is minus 2, 1. With a new basis, we get a new coordinate system. And let us introduce the coordinate vector of our unknown vector u with respect to basis b. And suppose this coordinate vector, let's call it f and g. And so in fact, f and g will be functions of t. What this says is that our vector u is a linear combination of basis vectors with coefficients f and t. So we have f of t times v1 plus g of t times v2. Next, let us substitute this expression for u in our differential equation. Here, the coefficients are functions of t, but the vectors themselves are constant vectors. So these are fixed eigenvalues of our matrix A. Then the left-hand side will look in the following way. So if we take the derivative of u, then we get f prime of t times v1 plus g prime of t times v2 is equal to the right-hand side. So we have f of t times a v1 plus g of t times a v2. But the vectors v1 and v2 are eigenvectors of matrix A. So this means that a v1 is equal to minus v1, and a v2 is equal to minus 5 v2. So the right-hand side will become minus f of t times v1 minus 5 g of t times v2. Now let us move everything to the left-hand side. We will get f prime of t plus f of t times v1 plus g prime of t plus 5 g of t times v2 is equal to 0. But our vectors v1 and v2 are linearly independent. So here we see that these two vectors are not proportional and non-zero. So this tells us that we can equate both coefficients to 0. So this means that f prime of t is equal to minus f of t, and g prime of t is equal to minus 5 g of t. From calculus, we know how to solve this kind of differential equations. If we know that f prime of t is equal to a times f of t, then this tells us that f of t is a multiple of the exponential functions. It's constant times e to the at. Indeed, when we differentiate this function, the constant a will be pulled out in front, and we will get the derivative of f is equal to a times f. So from here, we get that f of t is equal to c1 e to the minus t, and g of t is equal to c2 times e to the minus 5t. Now we obtain the solution for our problem, that the column vector x of t, y of t, which is our vector u of t, is equal to f, which is c1 e to the minus t, times v1, which is the vector minus 2, 3, plus g, which is c2 e to the minus 5t, times the vector v2, which is minus 2, 1. Now, extracting the components in this vector equality, we get our answer to this problem, that x of t is equal to minus 2 c1 e to the minus t minus 2 c2 e to the minus 5t, and y of t is 3 c1 e to the minus t plus c2 e to the minus 5t. And the constants here, c1 and c2, are arbitrary. This describes the solution set of this system of linear differential equations. Let me give you the following exercise. Let Fn be the space of vectors of the form x1 of t dot 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 xn of t, where xj of t are differentiable functions xj of t from R to R. Fix an n by n matrix A, and let U be the set of solutions of differential equation u prime of t is equal to a u of t, where this vector u belongs to Fn. Show that this set U, the set of solutions of these differential equations, is a subspace in Fn. So this would mean that if we take two solutions of this system of differential equations, then their sum is again a solution. Or if we take a solution of this system of linear differential equations, then the constant multiple of that solution is again a solution. In this example, so we see that we have two free parameters that describe this set of solutions. So this means that the set of solutions of this system of linear differential equations in this example is two-dimensional. Let us present two alternative approaches to this solution that are based on matrix diagonalization. So suppose we diagonalize the matrix A, which is essentially what we're doing here. We write A as C times D times C inverse, where C is the change of basis matrix that's associated with this basis, and D is the diagonal matrix that has these eigenvalues on the diagonal. So let us plug this into our equation, which is u prime of t is equal to a u of t. So then we get u prime of t is equal to c times d times c inverse times u of t. Now, let us multiply both sides by c inverse on the left. So then we get c inverse u of t, and all of that prime is equal to, so if here we multiply this by c inverse, this factor of c will cancel, and we get d times c inverse u of t. Then set c inverse u of t, so let's call it this w of t, and write it as a vector f of t and g of t. Then we see that the differential equation on w of t will be w prime of t is equal to d w of t. And here we have a great advantage because d is the diagonal matrix. So what we get is that f prime of t, g prime of t is equal to the diagonal matrix with eigenvalues on the diagonal, -1, 0, 0, -5, times f of t times g of t. And this equation immediately gives us that f prime of t is equal to minus f of t, and g prime of t is equal to minus 5g of t. And again, we arrive at the same solution for f of t and g of t. Really, these two methods are the same, because the matrix C inverse is a change of basis matrix from the standard basis to basis B. And so then our vector W, which is change of basis from standard to basis B applied to U, which is the vector in the standard coordinates. So then we see that in the right-hand side, we just have B coordinates of a vector U. And so our vector W is nothing but as coordinates of U taken with respect to basis B, which is exactly what we previously did. The third approach to solving systems of linear differential equations is based on the following idea, that if we know that f prime of t is equal to a f of t, this tells us that f of t is equal to constant times e to the at, where the meaning of this constant is the value of f at 0. Because if indeed we evaluate this function at t equals 0, then exponential of 0 is equal to 1, and then we get the answer as C. Now let us generalize this to a vector situation. So we have u prime of t is equal to a u of t. Then we claim that the solution of this system of differential equations is given by u of t is equal to e to the at times u0. Now this solution involves exponentiating a matrix, and this vector u0 is the vector of initial data. So this means that this is the value of the function u at t equals 0. Now let us discuss how can we exponentiate a matrix. So first we recall what is the usual exponential. So for the usual exponential, one way of defining it is using the Taylor series. So this is 1 plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial, and so on. The same can be done for matrices as well. E to the at is equal to, well, instead of 1 we should write identity matrix plus matrix A times scalar parameter t plus matrix A squared times t squared over 2 plus the cube of a matrix A times t cubed over 3 factorial, and so on. It turns out that this series of matrices will converge for any value of t. Well, one way is defining an exponential, and another thing is computing the exponential of a matrix for practical purposes. How can this be done in case when the matrix is diagonalizable? So what we have is that e to the at is the sum k goes from 0 to infinity, a to the power k times t to the power k over k factorial. If matrix A is diagonalizable, then we can substitute here the expression cd times c inverse. So we get the sum, k goes from 0 to infinity, c times d times c inverse to the power k times t to the power k over k factorial. We saw earlier that when we compute cd c inverse to the power k, so this gives us cd c inverse times cd c inverse, and so on, cd c inverse. And we saw that all the middle factors of c will cancel out. And so this is equal to c d to the power k times c inverse. Let us use this relation here. So what we see is that we can write this as c times the sum k goes from 0 to infinity d to the power k times t to the power k over k factorial times c inverse. And then the middle term becomes the exponential of the matrix D. So what we get is c times e to the dt times c inverse. And the point here is that for diagonal matrices, the exponential is easy to compute. So if we have a diagonal matrix D with eigenvalues on the diagonal, then e to the dt is going to be a diagonal matrix with e to the lambda 1t, e to the lambda 2t, e to the lambda nt, and zeros elsewhere. This can be immediately obtained from the definition of exponential, because here we know that d to the power k will have lambdas to the power k on the diagonal. And then this formula for the solution of the system of linear differential equations can be also written as u of t is equal to c times e to the dt times c inverse times the vector of initial values u0. As our next example, let us solve this system of linear differential equations with initial data that x of 0 is equal to 1 and y at 0 is equal to 0. So here we form the matrix that corresponds to the system of linear differential equations. So this matrix will be 0, -5, and 1, -2. And then the system can be written as u prime of t is equal to a u of t. If we can diagonalize matrix A, then we can write the solution in this form. So let us see. The characteristic polynomial of this matrix is lambda squared minus trace of A, so times lambda, so this will be plus 2 lambda, and plus determinant of this matrix, and the determinant of this matrix is equal to 5. We can solve this quadratic equation, and we will see that the roots of this polynomial are complex. They are -1 plus -2i. This tells us that this matrix cannot be diagonalized over real numbers, but can be diagonalized over complex numbers. Let us find the eigenvectors. And we start with the first eigenvalue, which is -1 plus 2i. So here we have to consider matrix A minus -1 plus 2i times identity. And so we subtract from diagonal entries this complex number. So we get 1 minus 2i, 5, and 1, and -1 minus 2i. Since we have an eigenvalue here, the determinant of this matrix is equal to 0. And this tells us that the rows in this matrix are proportional. So thus, the reduced row echelon form of this matrix is 1 minus 1 minus 2i, 0, 0. And we conclude that the first eigenvector that corresponds to this eigenvalue is going to be 1 plus 2i, 1. And then we apply our principle that the second eigenvalue is a complex conjugate of this one. So then, to obtain the second eigenvector that corresponds to lambda 2, we take the complex conjugate of this vector here. So we get 1 minus 2i and 1. So this is the second eigenvector. So we get that the change of basis matrix is the following. So we have 1 plus 2i, 1, and 1 minus 2i, 1. And the diagonal matrix will be the matrix with eigenvalues on the diagonal. And we need to put them in the right order. So we have -1 plus 2i, 0, 0, -1, minus 2i. And then the solution is given by this formula. Well, what is the vector u0 here? So the vector u0 is u evaluated at 0. And so this is the vector x of 0 and y of 0. And in this problem, we are given the initial data. So we are specified that x of 0 is equal to 1 and y of 0 is equal to 0. Let us write down what is the exponential of dt. So this will be the following matrix. So this will be e to the -1 plus 2i times t, 0, 0, e to the -1 minus 2i times t. But then this also can be written as e to the minus t times e to the 2it. And to compute this, we will apply Euler's formula. And here we have e to the minus t times e to the minus 2it. If we put all the ingredients in this formula, so the matrix C, this exponential of dt, and C inverse and this vector 1, 0, then we will obtain that our solution u of t is given by the following vector with these two complicated components. I leave the details of this calculation for you as an exercise. Well, it looks like we are in trouble here, because our original problem was completely real, so there were no complex numbers in this problem. So we don't expect complex numbers in our answer. Yet, as it is written here, there are lots of complex numbers that appear. Let us look for our expression for y of t, and let's try to simplify it. So here we have minus I over 4 times e to the minus t times e to the 2it minus e to the minus 2it. Here we can apply Euler's formula. So this is minus I over 4 e to the minus t times cos of 2t plus I sine of 2t minus cos of 2t plus I sine of 2t. And so what we see here is that cos will cancel and sine will double. And so what we get is minus I over 4 e to the minus t times 2I sine of 2t. And the final result, so I times I will be minus 1. So we get 1/2 e to the minus t times sine of 2t. And we see that our final answer for y of t is completely real. Likewise, for x of t, the answer is real as well. And again, I leave it for you as an exercise. So here the answer will be e to the minus t times cos of 2t plus 1/2 sine of 2t. This expression with complex exponentials, by applying Euler's formula, will simplify to this trigonometric expression. In conclusion, let us discuss the topic of stability of equilibria. If we have a system of linear differential equations, u prime is equal to a u of t, then we saw that the set of solutions is a subspace. This tells us that we have a constant zero solution. So if we take u of t to be constant 0, then this is a solution which may be interpreted as an equilibrium. So this means that this is a solution that does not evolve in time. We're interested in understanding what happens to solutions if we move away from the equilibrium. So if we are not in the equilibrium point, then our solution will evolve, and we want to understand whether our solution will approach the equilibrium or it will move away from the equilibrium. So if we're approaching the equilibrium at t going to infinity, so this solutions or this equilibrium is called stable. And if we are moving away from the equilibrium, then this is called unstable. What we see that our solutions are given by the following formula. So it's c e to the dt times c inverse times the vector u0. The evolution of this solution is determined by the exponential of the matrix D. Now, let us look at this matrix. What will happen to this matrix if t goes to infinity? So we see that when t goes to infinity, this exponential e to the minus t will make this matrix go to 0, because this Euler exponential function has a complex norm equal to 1. And why did we get the negative sign in this exponential? This negative sign, so e to the minus t, came from the real parts of the eigenvalues. So we get the following conclusion. If real parts of all eigenvalues of A are negative, then the equilibrium is stable. If there exists an eigenvalue lambda with a positive real part, then equilibrium is unstable. The question of stability of equilibria is very important for engineering applications. So typically, if you have something like an airplane or a washing machine, then the parts will be vibrating during the movement. If an equilibrium state of an airplane is unstable, so this will mean that during the vibrations, the amplitude will be ever increasing and the airplane will fall apart. And the analysis, whether equilibria are stable or unstable, use linear algebra and are based on this principle.